When we're using a point estimate based on an experiment to come up with a point estimate of the lambda for our population, part of the challenge is knowing how long to run the experiment and when we should stop. When is the lambda we get from an experiment good enough to be able to generalize about the population of products or services that we're describing? So let's take a quick look at a very, very simple experiment where we start off with 20 successes and we run them through a series of tests for an event that we've chosen to measure as on a scale of days. So if I begin that process, I might, after 7 days, note that I've had one new failure. So the one new failure says my mean time to failure is now 7, one failure in 7 days. I have 19 successes left, and the lambda I would get from my total formula would be 0.0071 with a mean life of 140 days. Now, trying to stop an experiment after only one round would certainly not be advisable to almost anybody, but hypothetically you could if you wanted. So you could take that new lambda of 0.0071 and plug that into a distribution based on the exponential distribution with that as our lambda, and come up with a curve and start to calculate the probabilities for what happens under the population of data that looks in that way. The predictions you'd get would be pretty unreliable since we really didn't run the experiment very long, but in theory, we could now talk about, with a lot of inaccuracy, the population in general. More realistically, what we would do is continue to run the experiment, maybe out to 10 days where 2 more fail, and we start to get a different lambda as our rate goes out. And at each stage, we could be plotting the lambda, including the graph here for the previous one, to show that we're getting an exponential distribution that might start to fit our population even better as we go on. We continue to run the experiment out to 16 days. We now have another failure, so we have 4 total failures, and our lambda now is 0.0134 for a mean life of 74.8. And again, you might have a preconception of what your engineers are telling you the mean life of the product is, and you can use that to help guide you as you start to continue your experiment. Till you get to the point where your data is pretty close to what you expect it to be, you might choose to censor your experiment at that point. Based on this 0.0134, we might plot our lambda again as we go through and find that that curve is starting to become a more accurate depiction of what we have going on. We then run to maybe a 22-day cycle of 0.0152. Notice the lambda here is back to what it was after the second experiment. So when I actually graph it, I don't get a new line. I have 2 versions being graphed on the same line here as I go through. So maybe that's significant that I ended up back with the lambda I had earlier in the experiment. But I continue my experiment out to 23 days. My lambda continues to revise now at 0.0171 at 58.4 days mean life. So I'm starting to get another curve in my data. So I'm constantly running my experiment, recalculating my lambda and my mean life, and then replotting the data across the curves to see what I get. I might choose to stop maybe at 39 days. I have no new failures, but I've chosen to stop the experiment here. So my lambda formula now gives me a 0.0210. So I have 0.021 failures per day for a mean life in days of 47.7 days. So these 2 values become my point estimate for the lifespan of this product. And I was able to come up with that in only a 39-day experiment, even though out of my original 20, only 12 have failed as I go through. But that might be a reliable number. So the question is, how reliable is it? Again, I go back to my curve of all my different data. I see all of these different curves, and it's hard to tell from the early data, but here's the data for the very last experiment with a 0.02097 lambda. And so notice I get a lot of variation here in the early days. And if you focus too much attention on that early data, you might want to run your experiment longer to try to figure out what the real value is, because it's been bouncing within this range. And maybe that range is acceptable. But notice to the right of the curve here, no matter what this lambda is, the exponential curve falls out to a pretty clustered approach as you get out past, in this case, about 55 days. So depending upon your scale and what you're trying to predict, you do reach the point where more accuracy on your lambda doesn't really help, because no matter what your lambda ends up being within the range that you're seeing this kind of oscillation, it turns out that the far right end of your curve, the tail, if you will, starts to stabilize quite a bit in the exponential distribution. That unless you're really trying to predict things in the short term, you don't need to do exhaustive experimentation to come up with a reasonable estimate of lambda for your population. Notice I'm not saying the absolute or correct lambda, I'm only saying reasonable. The estimate you come up with only has to be reasonable for the work you're looking to do with with it. You can always continue the experiment longer and get a more accurate number. But sometimes you just can't run the experiment that much longer, or people have to start using your data to drive projects. So even if you continue to run the experiment over the next 30 days, 60 days, 90 days, it's not that inadvisable for someone to start using this value during that period to start doing some preliminary engineering. You could always go back to them later and say, I have a better point estimate now of lambda. Here's the new value I think you should use. But a lot of that comes from the fact that the tail of the exponential distribution flattens out pretty well. And as you increase an experiment like this, what you find is you're going to be bouncing within the range that if the experiment shows random samples and it's a realistic picture of the system you're testing, you're going to keep getting lambda values that oscillate within a given range and aren't really going to change the long-term prospects that much. And that's one of the reasons we can censor an experiment or a test and cut it short of waiting for all of the products to fail.